In this video, we'll be taking a look at the functional group esters. Let's start our overview by looking at esters and the methods of preparation of esters or synthesis of esters, and then we'll take a look at different reactions of esters. And for our video, an ester consists of just a carbon residue that is attached to a carbonyl, a C double bond O, which in itself is not a functional group, but when we attach it to some other arrangement of atoms, in this case an oxygen and another carbon residue, we're left with an ester functional group. Because we are in the unit for the carboxylic acid derivatives, at this point in your videos, you're likely to realize that there is a way to interconvert between every single one of these carboxylic acid derivatives. And so keeping in mind that anything to the left of this carboxylic acid reactivity chart, and because it's the most reactive, their ability to synthesize anything to the right of it that is less reactive, esters fall right in the middle of that chart. And so a number of different carboxylic acids and carboxylic acid derivatives can be used to synthesize an ester. First and foremost, you may remember from another video that under reactions of carboxylic acids, that carboxylic acids can be esterified under acidic conditions or under basic conditions to synthesize an ester. And now in this video, we won't spend any time talking in depth about the reaction mechanism or the roles the reagents play in this transformation. We've done that extensively in the video for the reactions of carboxylic acids / preparations of esters portion of that video. And so go check out that video for a more in-depth look at that, the mechanism and roles there. Keep in mind, every single one of these interconversions between carboxylic acid derivatives is a nucleophilic acyl substitution reaction. And so if you understand the mechanism, you'll be able to use that in a number of different arenas. And esterifying carboxylic acids is one way of preparing esters. Another method is to esterify an acid chloride, an RC double bond Cl. And that functional group can again be converted into a ester through an esterification process. And again, because this is also can be considered a reaction of acid chlorides, please go to that video, and specifically the portion of that video that discusses the synthesis of esters, for a much more in-depth look at the mechanism and the roles that the reagents play here. And I just mentioned it, but I'm going to continue to harp on this idea that because we are interconverting between carboxylic acids and their derivatives, an acid chloride to a carboxylic acid, the mechanism is going to be the exact same as any other carboxylic acid derivative, and so you'll see a lot of commonality there. And we know from our studies up until this point that if we can use more reactive carboxylic acid derivatives to synthesize esters, and we've taken a look at acid chlorides, well, anhydrides are also fairly reactive forms of esters. Carboxylic acid derivatives, and and since they're reactive, more reactive than esters, they too are subject to esterification under the right conditions. And just like the previous examples, check your notes for the reactions of acid anhydrides, preparation of esters, for a more in-depth, detailed look at the mechanism and the roles that go into that functional group conversion. Same mechanism, Same way of interconverting. Another place to look for these ideas would be to look at the carboxylic acids and their derivatives video, the overall video that talks about how to identify your reagents just based on the interconversion that you're looking at. The other way to synthesize an ester is through just a substitution reaction. Rather than all of these esterification reactions that occur above, where you are using the carbon of the carbonyl as an electrophile, in this example here, we'll actually be using the oxygen of the carboxylic acid as a nucleophile, so that carbonyl carbon will remain absolutely unperturbed. It will not change. No chemistry will take place there. We will simply deprotonate that carboxylic acid first, which turns it into a decent enough nucleophile for these purposes, and then substituting an alkyl halide with that decent nucleophile is enough to synthesize an ester. So just be aware that the carbonyl chemistry does not change. And because that's just a normal substitution reaction, SN2 reaction, we won't take a look at its mechanism in any of these videos. That's something that you're intimately familiar with from your studies. Now, if we shift gears and take a look at the different reactions of esters, esters are a family, a subgroup of the family of carboxylic acid derivatives, and therefore the reactions that undergoes are nucleophilic acyl substitution reactions. And as you've seen before, the idea here is whether or not that nucleophilic acyl substitution has occurred once or if it's occurred multiple times. And in this example here, if that nucleophilic acyl substitution happens one time, we can synthesize a number of different carboxylic acid derivatives that are less reactive, as well as a carboxylic acid. And so what you see drawn first there is the hydrolysis or the hydration of an ester and conversion of that ester into a carboxylic acid. And where we've seen this before too with different carboxylic acid derivatives and their reactions with amines, we can amidate an ester and synthesize amides, primary amides or secondary amides through amidation of an ester. And so be aware that is also a possibility using the same nucleophilic acyl substitution. Same ideas in other videos, and hopefully by now you're starting to realize that I'm not teaching you anything new. It's just a variation on a theme. If you can see this done with an oxygen, you can see it done with a nitrogen. Here we're looking at the use of a hydrogen atom and a reduction, and I keep calling it a reduction in these videos, but it really should be a substitution. I'm not comfortable with that. But regardless of the name there, we can synthesize an aldehyde through this reaction mechanism as well, using one nucleophilic acyl substitution reaction rather. And then as you've seen before, if we use multiple iterations of this nucleophilic acyl substitution reaction, and usually follow that up with protonation at the end, we can synthesize alcohols, and specifically primary and tertiary alcohols. You've seen this with acid chlorides, you've seen this with anhydrides, and so again, variation on a theme, same type of chemistry, we just have a different carboxylic acid derivative. And so when you're taking a look at the mechanism and the roles that the reagents play here, we won't discuss those in this video right here because you've seen this before. So take your attention to the reactions of acid chlorides / synthesis of alcohols for a discussion on that, or you could take a look at reactions of acid anhydrides and synthesis of alcohols for the roles and mechanisms that would be applicable to this reaction as well. In this video, we will be taking a look at nucleophilic acyl substitution reactions that occur on the ester functional group. And you may encounter this as part of your reactions of esters studies or as your preparation of carboxylic acids, preparations of amides, or preparation of aldehydes from esters in your studies. Let's take a look at the generic reaction scheme. And for this, we are going to model this reaction using an ester where we have a carbon residue that is denoted as R attached to a carbonyl, and then an O and an R prime carbon residue, something different, and subjecting that to nucleophilic conditions, either catalyzed by acid or base, to substitute out a nucleophile for that ester. And so for this, we are looking at the nucleophilic acyl substitution reactions of esters that occur in one time. We get a substitution, not a reduction. And so this is starting with esters. What can we make? Once we introduce the functional group that is being transformed and the conditions, and the name of the reaction, nucleophilic acyl substitution, well then let's talk about the regiochemistry. And just like all other nucleophilic acyl substitution reactions of carboxylic acids and their derivatives, the chemistry is changing on the carbon of the carbonyl, and so that's where the regiochemistry is taking place. The products that we make using this mechanism only once are sp2 hybridized at that carbon where the carbon change, the chemistry takes place, and so we don't have to worry about the chirality. So taking a look at the different types of functional groups that can be generated using this method, if we're in this realm of carboxylic acid derivatives and we want to take those derivatives and make other carboxylic acid derivatives, well, we can only directly synthesize the ones that are less reactive, and we can only synthesize the carboxylic acid from any derivative. And so if we hold true to those rules, then we can synthesize carboxylic acids from esters if we were to subject them to water in either basic or acidic conditions. And this reaction has a bunch of different names: saponification, hydrolysis, or hydration, to produce carboxylic acids from esters. This is what happens to cooking oil when you fry things with it. You're adding water to hot oil, which is enough to start to take esters in fat and convert them into carboxylic acids, soaps. This is also true for amides. Amides are a very important class of bonds from esters because they make peptides. And using just a primary amine or ammonia or a secondary amine, they can be added to an ester to convert them into primary, secondary amides, as well as regular amides, through a process called amidation. And the last type of substitution reaction, and again I'm going to write reduction, it should really be a substitution reaction, using this molecule called DIBAH in the presence of water to synthesize this aldehyde. And you may be thinking, oh man, here's an example now of this, a new reagent in order to make some transformation occur. But if you know what DIBAH is and what it affords, then the chemistry is rather straightforward. DIABH is, it stands for diisopropyl aluminum hydride, and that molecule affords us an H minus. And so if you see DIBAH, you're thinking to yourself 1 molar equivalent of H minus. Regardless, that will undergo a substitution type reaction and convert an ester into an aldehyde. Let's take a look at the roles that the reactants play in this transformation. Here we're going to use the same generic ester, which will behave as an electrophile at that carbon of the carbonyl. The nucleophile that we add, this is from the Department of Redundancy department, that will behave as a nucleophile, of course, and then your acid or base will behave as a catalyst. And we'll be taking a look at 2 different methods of catalyzing a hydrolysis reaction in just a second. The end product here would be substitution with that nucleophile where the OR portion of our ester was. Let's take a look then at the reaction mechanism. For this, we are going to convert an ester, methyl benzoate, into benzoic acid. And the first mechanism we're going to take a look at is this reaction conversion taking place under basic conditions. These would be the conditions that are used to make soap. And so you're simply adding lye and water to some sort of fat, which is an ester, to make carboxylic acid. This reaction mechanism is very straightforward because it utilizes incredibly strong nucleophilic conditions, sodium hydroxide, something you wouldn't want to add to your body at all. That's going to have a very strong nucleophile, and that carbonyl of your ester is your electrophile, and like we've seen before, nucleophilic attack will occur on that carbon of the carbonyl, and we will form a tetrahedral intermediate following that nucleophilic attack step. That tetrahedral intermediate then is really is reactive, and it wants the molecule's tendency is to reform the carbonyl, and in order to push the reaction forward, the leaving group would have to be the OCH3 portion of the molecule. And so if we consider that a leaving group, the reformation of the carbonyl will displace that methoxide leaving group and generate our carboxylic acid as a result of that loss of leaving group step. Now, it begs the question, well, why not just remove the OH again? Well, the reason for that is that you're going in reverse. And if one of those leaving groups isn't preferential, how do you drive this reaction forward chemically? Well, you just have copious amounts of hydroxide present. We're talking about thousands of molar equivalents more. So that in the event that the OCH3 leaves the molecule, the chance of that carboxylic acid finding that methoxide anion are very low, because there are just thousands and thousands and thousands, millions even, of water molecules surrounding it in hydroxide anions. And so we control it just by brute force in that manner. You can run the same esterification under acidic conditions, which is likely what's happening in cooking oil when we use it to fry foods. Many foods are slightly acidic, and so that affords protons that allows us to cleave fats and make carboxylic acid. So if you were paying attention to what I was just saying, yes, when you fry foods, you start to make soap. It leads to the rancidity of your oil, but you're likely eating a few molecules of soap every time you eat fried food. Small price to pay, though, for fried foods. This reaction mechanism, I'm a little bit behind the mechanism, but I'll catch up here. The reaction of that methyl ester with acidulated water is a Bronsted-Lowry acid-base reaction, and whenever we add a proton to a functional group, the first thing you ask is look for is you find the lone pairs of electrons on a heteroatom and add a proton to it, and the most receptive lone pair of electrons are the ones on that oxygen. Once that carbonyl is protonated, the reason why we do that is because the electrophiles that we typically use in acidic conditions are weaker. In order to improve reactivity, the best thing to possibly do is increase the electrophilicity of the molecule if the nucleophilicity is decreased. And so protonation of that carbonyl makes it a better electrophile, much more suitable for nucleophilic attack with water. Once we've done that, we've formed a tetrahedral intermediate, but the water molecule that just added is the best leaving group, and we want to flip that scenario to make the methoxy portion of the tetrahedral intermediate the better leaving group. And in order to do that, we need a quick Bronsted-Lowry acid-base reaction to deposit the proton from the water leaving group on the methoxide leaving group, in turn making the methoxide the more preferential leaving group, the protonated methoxide, and the hydroxyl the better staying on group. Keep in mind, again, with those Bronsted-Lowry acid-base protonation steps, they could occur intramolecularly, which is the way I typically draw them, but they could also occur intermolecularly as well. Once that methoxide I did it again. Methoxide is protonated. It is now a very good leaving group. Reformation of the carbonyl with either one of those alcohol lone pairs will displace that leaving groups as methanol, and then all that you're left with is a protonated carboxylic acid. And at that point in the reaction, it's completely done. You'd pour it into a separatory funnel with a small amount of water and sodium bicarbonate, and that would be enough to deprotonate that protonated carbonyl through a Bronsted-Lowry acid-base reaction here, a deprotonation step that I'm going to show using water to generate our final deprotonated carboxylic acid. When you look at the substitution of esters with amides and with this diisopropyl aluminum hydride, you will find that those occur in a basic type mechanism with proton transfers there, rather than this acid catalyzed one that we just went over.